Long before we learned to beat the air into submission, there was a quieter path. Archimedes discovered that an object immersed in a fluid experiences an upward force equal to the weight of the fluid it displaces. It is the physics of absolute buoyancy. In 1670, Francesco Lama de Terzi applied this to the sky. He proposed evacuating all air from hollow copper spheres to create a vacuum. Since a vacuum weighs nothing, the spheres would be lighter than the surrounding atmosphere, rising naturally into the firmament. Humanity took a different direction. Instead of seeking natural buoyancy, we built machines that fight gravity by burning fuel. Whether it is a jet engine or a rocket, flight today relies on expending enormous amounts of energy to push against the air. Lana de Terzi's copper spheres were never built. For over 200 years, the vacuum airship remained a theoretical curiosity, as every attempt to construct a functional prototype ended in failure. The barrier to fuel-free flight was a specific mathematical limit within the laws of physics, one that dictated the exact point where a structural material fails. Standard atmospheric pressure at sea level is 101,000 pascals. That places roughly 10 metric tons of force on every square meter of a vessel's surface. A vacuum ship must resist this crushing weight without collapsing. Spherical shells resist this pressure by bending. The curvature of the wall converts the inward push into a complex field of stresses that travel through the material. To be light enough to float, the sphere's walls must be paper thin. But at that thickness, the material cannot resist the atmospheric crush. It crumbles. The sphere fails to float and instead implodes. In 1915, Richard Zoli derived the equation for this collapse. His math showed that an aluminum sphere thin enough to float has a safety factor of 0.0015. It will buckle at a tiny fraction of the required load. Increasing the wall thickness provides the necessary strength to survive the pressure, but the added weight makes the vessel too heavy to rise. The two requirements, lightness and strength, are mutually exclusive in a sphere. The engineering failure was a consequence of the geometry itself. For 2 centuries, designers assumed the vessel must be a continuous, curved shell, but the math of shells under pressure makes buoyancy impossible. To move past the buckling limit, the design must pivot away from continuous shells and toward a lattice of straight lines. A tetrahedron consists of 4 triangular faces and 6 straight edges. Pressure applied to any face resolves into pure axial compression along its edges. There is no bending. Each strut is simply pushed from both ends, redirecting atmospheric load where materials are strongest. The buckling of these straight struts is governed by Leonhard Euler's equation from 1757. It allows engineers to calculate exactly how much force a column can carry, based on its length, stiffness, and cross-section. This lattice architecture decouples gas containment from the structural load. The struts carry the atmospheric crush, while a thin skin merely seals the vacuum. This allows for buckling resistance without adding non-buoyant weight. While a spherical shell fails with a safety factor of 0.0015, a tetrahedral lattice made of carbon fiber provides a safety factor of 6.3. This provides a structural margin more than 6 times the maximum atmospheric load. This math was verified in a domestic kitchen. The Moonball is a 74mm tetrahedron, 3D printed with carbon fiber polymer and heated in an oven to 200 degrees Celsius to expel the internal air. Once sealed with a steel ball bearing and cooled, the resulting internal pressure drop creates a partial vacuum. The object displaces more air than its own mass, causing it to float silently without any external power source. The Moonball proved that vacuum buoyancy does not require exotic materials or massive government labs. It requires a specific geometry that uses straight-line compression to survive what curved surfaces cannot. The physics of the lattice improve as the structure grows. Because volume scales as the cube of the dimension while surface area only grows as the square, larger vessels gain net lift far more efficiently than smaller ones. This principle is tested through the neutral cell challenge. Builders use off-the-shelf carbon fiber tubes and 3D printed nodes to construct 3-meter geodesics. When evacuated, these 17-kilogram structures achieve neutral buoyancy, registering exactly 0 on a load cell. Tiling these cells creates the Merkaba Dragon. It is a 30-meter atmospheric water harvester that uses cooled dorsal scales to condense vapor into droplets. A 40 Hz acoustic resonator then vibrates the air, causing those droplets to coalesce into rain for delivery to the ground. The Dragon moves through solid-state peristalsis. Peltier heat pumps expand and contract the gas within the vacuum cells, creating a traveling wave along its spine. This anguilliform locomotion allows the vessel to swim through the air without rotors, bearings, or gears. By making the engineering blueprints public domain, the architecture of flight is no longer restricted to those who control the fuel supply. The sky is now open to anyone capable of building with the geometry of the tetrahedron.